Thanks a lot. So I'm also extremely grateful to the organizers for setting up this important event, I think for many of us, all of us, especially the ones who knew Jean-Pierre quite closely as former students in particular, so that was my case. And yeah, so this is very moving, I think, at the moment. Many memories come back. And yeah, I just wanted to point out something many of you saw on the glass, this on the cup, this duality between the pseudo-effective cone and the movable cone of curves. So that was a highlight at the end of my PhD when Jean-Pierre finally nailed down what became his BDPP paper. So yeah, he was extremely generous to include me as an author and as an illustration of this great generosity that has been emphasized by so many people. Okay, so well, it's not a happy event, but it's great to see, of course, Jean-Pierre's math keep on influencing the whole field, and for sure this is going to last for a long time still, through his books, all these fantastic results. Okay, so what I'm going to talk about today is not directly related to that, I suppose, but I mean, it's Kähler geometry anyway. And okay, so that's a joint work with Mattias, Jonsson, and Antonio Trusiani, where we revisit previous works, in particular by Arezzo, Pacard, and Seyyadili-Szekelyhidi, on the existence of extremal metrics on blowups of a manifold, if you have such a metric on the manifold itself. So of course I will recall what these metrics are and so on. Okay, so my setup is that of a compact Kähler manifold, non-singular. So actually the most interesting case would indeed be that of a singular guy, but I will say a word about this at the end of the talk, but that's not what I'm assuming here. It's non-singular, and as we know, so the volume form omega to the n corresponds to a metric on the canonical bundle, or equivalently on its dual, which is just the determinant of the tangent bundle. And the curvature of this metric for the Chern connection is called the Ricci curvature of omega. Okay, so that corresponds to this curvature of this metric. That one. Okay, and in particular, this tells us that the Ricci form is a closed 1-1 form that represents the first Chern class of X, at least if you normalize the curvature correctly, so as to absorb the 2 pi factor. That we do. Okay, and then the next thing we want to look at here is the scalar curvature. Scalar curvature of omega. It's just, so this is the usual Ricci curvature of Riemannian geometry, but just has this nice interpretation in the Kähler setting. And the scalar curvature is now the trace of the Ricci. So you get a small function on X, which equivalently can be rewritten thanks to this language of differential forms we can use here in this way. And now, so I guess, as we all know, omega is said to be Kähler-Einstein if it's an Einstein metric, which is also Kähler. So it means the Ricci is constant. The Ricci curvature is a constant multiple of omega. And well, one observation from the fact that the Ricci form represents C1 of X is that you get a cohomological constraint that the first Chern class has to be proportional to the Kähler class in which omega is living. And in particular, this forces the canonical bundle to have a sign, positive, negative, 0. So it can't exist if you don't have this sign assumption on Kx. Okay? And of course, well, that's probably useless to do here, but just recalling the basic examples of the Fubini's 2D metric on Pn, the flat metric on a complex torus, and the complex hyperbolic metric on a quotient. So these would actually be of constant curvature. The whole curvature tensor is constant, which is much stronger. Okay, so we can't always find a Kähler-Einstein metric for the very reason I mentioned before, that you need to have this proportionality condition. So then you can ask, okay, how about the scalar curvature? So the next problem is the CSCK problem, constant scalar curvature. So you say that omega is CSCK, and that's for constant scalar curvature Kähler metric. Well, if, of course, the scalar curvature is constant. But then the good news is that this constant, you know a priori, because it has to be equal to the mean value of S. And the mean value you can determine using the formula here. So the mean value, so that would be, you would be integrating this guy. So that's the mean value. But thanks to the formula over there, it's just a cohomological constant that you know beforehand. So the right-hand side of this equation is known a priori. But then, well, again, there are obstructions to get such metrics. I will say a bit more about that. So then the next candidate that Calabi came up with sometime later, I guess in the early 80s, is that of an extremal Kähler metric. And so here the condition is a bit strange when you first see it. So you don't require that S of omega is constant, but you want it to induce a holomorphic vector field. So you take the 1,0 part of the gradient of this function, and you want that to be a holomorphic vector field on X. That will be called the extremal. It will be denoted by Xext. That's a global holomorphic vector field. And the X is for extremal, so it's the extremal vector field. Okay, so why do you want to look at this equation? So the way Calabi came up with that is that he got that as the Euler-Lagrange equation of a functional. Euler-Lagrange equation of, you can take the L2 norm of the scalar curvature. So you vary omega inside of its cohomology class. You can write down the Euler-Lagrange equation and you get this. But you could do the same with, maybe it would be more natural perhaps to do this one. You want the best approximation to being CSCK. You look for critical points of that. And you get the same answer. So these are extremal metrics. So as we will see, they are much more flexible as far as deformation theory is concerned. So a key aspect is that if you have such a metric in a given Kähler class and you deform the Kähler class a bit, then it's a classical result by Lebrun and Simonka that you also have extremal metrics nearby, whereas for the CSCK, the analog in the CSCK problem is obstructed. Okay, and then the theme here will be to deform, but on a blow-up. You will want to pull back the rational model, deform a bit, and again show that you have an extremal metric on the blow-up. So one thing you can say about this situation here is that the extremal vector field is a killing vector field. It generates, it's an infinitesimal isometry for omega. So it will generate, it generates a compact torus Tx. If you take the flow of this guy, it's going to be the closure of the flow is an abelian compact Lie group, so it will be a torus, and that's a torus of isometries. Okay, of isometries of omega that you get for free. Okay. So now that there are obvious, there's a hierarchy of conditions here. So the Kähler-Einstein condition is the most strongest one. And so you can relate these various notions of canonical metrics. And you can actually tell exactly when you can pass. You can go back to the previous the stronger one. So of course, the Kähler-Einstein metric, the whole Ricci tensor is constant. So then the trace of that is also constant. So Ke implies CSCK. But Ke also implies this proportionality that I mentioned before between the first Chern class and the class of omega. And actually, that's the only obstruction. So you can. So if you assume this necessary proportionality condition, the two notions are really the same. And the reason for that is that you can compare the Ricci of omega and lambda omega. The error term will be dd bar exact, dd bar of a function. And the CSCK condition would tell you that the Laplacian of this function is 0. But then the function has to be constant. So you can go back, really. So it's not a different problem. It's really, Ke is a special case of that in the sense that exactly when the polarization, the given Kähler class satisfies the proportionality condition. And then CSCK, of course, it implies extremal. The gradient of the constant function will be the 0 holomorphic vector field. So then the torus will just be a trivial torus, of course. And here in a kind of tautological way, you go back when the extremal vector field is 0. But actually that corresponds to the so-called Futaki invariant being, I mean, not the so-called, the Futaki invariant being 0. So again, we have a sort of, I won't really enter that too much, but we have a sort of algebrogeometric condition that distinguishes exactly between these two cases. Okay, so now I want to tell you about the classical obstructions to the existence of such metrics and the question of uniqueness. Obstruction and uniqueness. So the two are related, and for that I need to discuss a certain group of symmetries that plays an important role here. So we consider the identity component of the group of automorphisms of X. So the group of automorphisms of X is a complex Lie group, and so is its neutral identity component. So of course, well, if X is projective, that's an algebraic group. If X is not, of course, this is not an algebraic group. But there is still an analog for this group of the Chevalet decomposition, or the Chevalet theorem that holds for any algebraic group, that it has a linear part and an abelian variety part. So this is still true in this transcendental situation, surprisingly. I mean, not the abelian variety, but so more precisely, there is a certain linear algebraic subgroup, which is called the reduced automorphism group of X. So that terminology is not, it's a bit local in the field. It might be due to Paul Goduchon, but I'm not even sure. It's sometimes called also the linear part of that. And then the quotient here is a compact, complex torus, which would be an abelian variety if X is algebraic. Okay, so this reduced group of automorphisms, it can look a bit strange, and the fact that it's algebraic is also a bit surprising at first, so that's based on quite deep results of, it's Fujiki, Akira Fujiki, who proved that in the late 70s. Okay, but now if you go back to the algebraic case, so assume that X is projective and L is ample. So usually for this CSCK problem and all that, we assume that the class of omega is actually the first Chern class of a line bundle. Then you have this algebrogeometric condition of K stability that you can use. But anyway, so then in that case, the natural thing you want to look at is the automorphisms of the pair, the polarized variety, XL. And this has a C star action on the fiber. And you can map this down to just automorphisms of X. So the kernel is simply this trivial, simple C star action on the fibers. And now it turns out that this group here is just the image of that. So the reduced automorphism group is just the image of this map here. So it means that it's exactly the automorphisms that lift to a polarization of X. And that's in particular independent of the choice of L. So it's the natural symmetry group that you want to use here. Because the thing is that in this Kähler situation, you can't say that you look at the subgroup of that fixes the Kähler class, because that's everybody. O0 acts in a trivial way on the in cohomology. So you still need a way to distinguish what's the right group. Okay, so if X, for example, is Fano, then you can take L to be minus K, and everybody will live to minus K. So then you get that O0 is the reduced automorphism group is everything in that case, and that's, of course, that's a linear algebraic group. And on the other end of the spectrum, if X is a complex torus, then the linear part is trivial, and you just got this part here, the compact complex torus. So in that case, the reduced automorphism group is trivial. Okay, so now we have this classical result, at least in the CSCK situation, and further extended later by Calabi to the extremal case. So that it's a result of Schneerowitsch, Matsushima, and later Calabi. So you assume that omega, assume that you've got some extremal metric omega on X. Then you look at the group of isometries, but the part that lies in this reduced automorphism group. So you denote by K the group of isometries of omega inside of this complex linear algebraic group, the reduced automorphism group. And then what the result says is that the complexification of this guy, which is a reductive group, is exactly this group here. So it's exactly the part where the centralizer of this extremal vector field inside of the reduced automorphism group. So in particular, if you assume that omega has constant Kähler curvature, which was the situation of Schneerowitsch and Matsushima, the extremal vector field is trivial, so that's the whole group. And what you get is that the reduced automorphism group, in that case, has to be a complex reductive group. Okay, and as a consequence of that, still in this extremal case, if you assume that omega is extremal, there will always exist some maximal compact torus T in the group that you want to look at, the reduced automorphism group that fixes omega. So why is that interesting? Is that it's interesting because you can then take things in the reverse order. You can fix such a T. Just look at extremal metrics that are T invariant, and then Xx is an element in the Lie algebra of T that can be determined purely in terms of determined a priori. In fact, in terms of the Futaki invariant I mentioned before. So it means that here you are looking, the equation here is not that S of omega is constant, it's S of omega has to be what is called a holomorphy potential for this extremal vector field, and the extremal vector field we know a priori. So it means that the extremal equation is also an equation for S of omega for which the right-hand side is known a priori, just like S bar in the simpler constant case. Okay, but then what's more important maybe is that this gives the first obstructions to the existence of the metrics in question. So I've mentioned before that Pn, of course, the Fubini-Studi, well, a Fubini-Studi on Pn is always Kähler-Einstein, so in particular CSCK and extremal. Then the next thing you could look at is you blow up P2 in one point, and already it doesn't have any CSCK metric, precisely because of this theorem I've just recalled. So as a classical example, if you blow up P2, CP2, of course, at a point, so that's the first irreducible surface, if you want, then the automorphism, so if x is that, then odd 0 of x, which will be, so that's a Fano surface, so you get odd 0 is odd r, and that's just things that preserve the, you get some block triangular matrices like that. Well, I guess just whoop. Okay, so you get some parabolic subgroup that corresponds to the automorphisms of P2 that fits point P. And this guy is not being parabolic, it cannot be reductive. It cannot be the complexification of a compact group. So that means that you will never find a CSCK metric in any class on X. So that doesn't exist any CSCK metric on X. But in fact, there exists an extremal metric in any Kähler class on X. So that's something that Calabi proved early on. And then he believed for a while that there might always exist extremal metrics in any Kähler class. So it would give you a notion of canonical metric associated to compact Kähler plus a Kähler class. But that was disproved not long after using this structure result that I just mentioned. So as another example, now you blow up, so that's something that's to Levine. So you blow up P2 a bit more. So a sequence of, so maybe 4 blow-ups or something like that. And then you can arrange that the automorphism group here will be a unipotent group. So it will be something like this. And such a group cannot contain any compact, non-trivial compact subgroup. In fact, you can arrange that to get C, I think. So, but this guy cannot contain any compact subgroup. Non-trivial, of course. And then you won't have any extremal metric on your X in X at all. Yeah, because this extremal metric, either it's the extremal vector field is 0, but then it's a CSCK metric, and the group should be reductive, but it's not. Or it's not CSCK, but then you have this torus I was mentioning before, the extremal torus that sits there, so it gives you another compact subgroup for free, and it cannot happen in this situation. So that's an early example where you cannot have any such metric. Okay. Then say it again, sorry. Can you repeat what sorry, it's a finite sequence of blow-ups, of point blow-ups. I think you blow up 4 points successively. 5. Wait, who cares? Yeah, some. Okay. Okay, but that's important because the theme of the theorem I will state slightly later is that if you blow up points that satisfy certain invariance condition, you will get an extremal metric on the blow up. So I mean, here you start from P2, it has an extremal metric, you blow up a number of times, and you don't have any extremal metric at all. So it means you have to blow up points that satisfy it. No, they're not generic. Yeah, it's a very explicit. Yeah. No, they are infinitesimal, infinitesimal. Yeah. Right. Sorry? That's right, yeah. Okay. So I said, so the groups we saw before, that they served to get some, obstruction to the existence of the metrics, but they also play a key role in uniqueness statements. So in fact, all the metrics above, so extremal metrics, are essentially unique, so as unique as they can. So if you take an extremal metric and you act by some automorphism of X, it would still be an extremal metric. So you can't really do better than that a priori. But in fact, they are unique modulo automorphisms. So that's much more recent, maybe 15 years ago. And Széyadili, that would be. So I'm not sure who wrote that in the extremal case and the generality I've got. Oh, sorry. I'm using notes in French. So extremal metrics in a given Kähler class omega are unique modulo the group of reduced automorphisms, in fact. But then you can do a bit better. As I said, what people do is, in fact, to use the point of view up there, you fix some maximal compact torus. So if you look at, if you fix some maximal compact torus T, and you just look at T-invariant extremal metrics, which is not really a loss of generality thanks to this corollary there, then the T-invariant extremal metrics in the given Kähler class are unique up to the action of a smaller group, which is just the complexification of the algebraic group TC. So it's better to be able to restrict the amount of non-uniqueness we've got here. So yeah, as I said, that's just some C star to the R sitting in this reduced automorphism group. Okay, so then I've mentioned before that so then I can state the results we want to get to. So one good aspect of extremal metrics, even though they don't always exist, is that they deform well. So this Lebrun-Simonka result says that if you look at the set of Kähler classes that contain some extremal metric, this is an open subset in the Kähler cone. So in other words, if you take an extremal metric and you deform its cohomology class a bit, then in nearby classes you still have extremal metrics. And as I said, this is not true in the CSCK situation. So it would be if you assume that X don't have any holomorphic vector fields, because then CSCK and extremal mean the same thing. So if you kill the automorphisms, then you're good. But in general, you have obstructions related to the Futaki invariant, etc. Okay, so that's not so hard to show, actually. So based on some implicit function theorem arguments, you linearize the CSCK, the extremal equation. And, well, you get that the kernel is 0, so you can use the implicit function theorem to deform the metrics. And then the other sort of deformation we want to look at here is Arezzo, goes back to the work of Arezzo Pacard. And then, Seyyadili-Szekelyhidi. And, okay, and then the thing we did that improves that slightly. So you assume, as before, that you look at X omega, you assume that omega here is extremal, and you assume it's T invariant for some maximal compact torus as before. And then you decide that you want to blow up something, but you blow up something that is T invariant, so the T action will lift. So pi is the blow up of some submanifold submanifold Z that is T invariant, complex submanifold, of course, that is T invariant. Then, as we know, if you pull back the class of omega and you subtract, so the exceptional divisor would be, I denote by E. Then minus E is pi ample. So if you subtract, okay, write this here. So you pull back omega, you subtract a small multiple of the class of E. This is ample when epsilon is small enough. And in fact, it contains, an extremal metric when epsilon is small enough. So it's like deformation, again, a sort of openness when you deform the class. But here you deform a class which is not Kähler anymore. You deform this semi-positive class, pullback of omega. So then, no. Just for all epsilon small enough. But say it again, sorry.
Is this if and only if condition?
Oh, you mean if you have such a metric and you get one downstairs? No, I don't think so. No, I don't think so. But so I guess, yeah, modulo the non-uniqueness problem. But for example, if you assume that there are no vector fields on X, then you don't have to worry about non-uniqueness anymore. Then, yeah, certainly that's true. Yeah. But I'm not sure if it's really written down in detail somewhere. So I should say that, so Arezzo, yeah, maybe I can say here. So Arezzo Pacard, they look at point blowups. But the result is actually more general because they don't insist that you just blow up things that are T invariant for a maximal torus. That's a strong constraint. So they have more flexibility. More work have been done in this direction. On the other hand, Seyyadili-Szekelyhidi, they blow up some higher dimensional center, but they have the technical condition that the codimension somehow has to be greater than 2, so at least 3. Well, just some technical thing that shows that in their proof. So of course, they believe that it could be gotten rid of, and that's a consequence of. So what both all these guys are using, the technique is, there's some gluing techniques to construct the metric. And okay, so I will explain the approach that we take, which is based on a variational characterization of extremal metrics. So the approach is based on the fact that extremal metrics can be realized, or their potentials can be realized as critical points of a certain functional. So I've mentioned before the Calabi functional, but it's not the one that people use here. Okay. And again. So the key input here, the key analytic input is a deep result of Chen and Chung, proved some maybe 5 years ago, 10 years ago, that provided this variational characterization of CSCK metrics. And then He extended that to the extremal case. So they say that there exists an extremal metric if and only if a certain functional is proper in some sense. And then what we try to show is that properness carries over to the blow-up. That's the approach we try to follow. And then one possibly good aspect of that is that this properness makes sense when X is singular. Then you can try to use a result like that where pi would be a resolution of singularities and try to produce, say, CSCK metrics upstairs and have them converge, as Henri was alluding to a metric downstairs. But that's something that is not really completed in any ways so far, but that could lead to interesting developments, maybe. Okay, so as before, I'm fixing some Kähler T-invariant metric, 1-1 form, where again T is my maximal torus. So now, as we know, the DD bar lemma of Kähler geometry tells you that you can parameterize all other Kähler metrics in the class of omega by functions, so-called Kähler potentials. So you look at functions, smooth functions phi, such that omega plus IDD bar phi is positive as a one form, and all Kähler metrics in the class of omega are like that. So this is the space of Kähler potentials. So the question is, can you find phi like that, such that omega phi is extremal? What do you? Okay, then the key aspect here is that there exists a functional, a canonically defined functional M for Mabuchi. So you just take the T-invariant part of that because you are just interested in T-invariant metrics. So this functional is defined on the T-invariant part. It's the Mabuchi energy functional. So sometimes it's called the K-energy, but then you can wonder why you would use M. It's the relative version actually in this extremal case, but you don't really worry so much about that. So this functional has the property that the phi is a critical point if and only if omega phi is extremal. Okay, so in fact, so the way you get this functional is not only by looking at this condition here, but you want the derivative of phi to correspond to the thing we saw before. So S of omega phi minus say this holomorphic potential of the extremal vector field. You look at the PDE that corresponds to omega phi being extremal, the PDE on phi, and you want the right-hand side, the derivative here to be equal to the corresponding differential operator. So if it exists, it's unique. You can get it by integration. And there's a fairly complicated formula for that I won't inflict to you in full, but I just want to mention a few pieces. Okay, so what we know about that. So first of all, this guy, M, a key aspect is that M is invariant under the symmetry group that we want to look at here, which is the complexified torus. We said before that extremal metrics under this invariance assumptions with respect to the maximal torus, they're unique with up to the action of TC. So TC is acting there, and the functional is actually invariant under this symmetry group. And then one other thing I want to say is that so there's an explicit formula that is usually called the Tian formula for this functional. So I'm just gathering the terms in two pieces. Okay, so maybe I'll write it here. So H of phi is the so-called entropy, the entropy part. So what it looks like is indeed the entropy of the corresponding volume attached to omega phi. So it looks like this. That's a non-negative quantity. And yeah, if you think that F is the density of omega phi to the n with respect to omega, the reference volume form omega to the n, then that's the integral of F log F. That's entropy. And the other guy, I will just generically call energy, but say, so in the sense of pluripotential theory. So the distinction here is that it behaves very nicely with respect to pluripotential theory indeed. So we'll see that it extends in a continuous way to a completion of the space of Kähler potentials, whereas that guy there is more nasty, and it's the tricky term to control in the whole story. Okay. So the next thing we need to formulate this variational characterization is that H comes with a canonical, with a metric. In fact, a family of metrics. It's here I'm considering the metric D1. It goes back to the work of Tamás Darvas. the D1 metric, so that's the length metric attached to the L1 Finsler norm on H. So the idea is that you pick a point in H, and it comes with a Kähler metric omega phi, and you have a corresponding L1 norm. So then you take a tangent vector, which is just some smooth function, and you want the length of this guy to be the L1 norm with respect to omega phi. So you could play the same game with, of course, with the LP norm, in particular L2, it would be not natural. But the L1 case turns out to be the one we need to ensure compatibility with pluripotential theory. So there's a metric like that. Then you can consider the completion of H. Again, the work of Darvash tells us that the H bar, the metric completion of HD, can be realized as the space of potentials of finite energy. So it's a space of singular analogues to the Kähler potentials we saw before. It's a certain class of omega PSH functions whose energy is finite. So there are functions, omega PSH functions. And a finite energy condition would be that the gradient is in L2 when n equal 1. That's the classical finite energy condition in potential theory in one complex variable. But in the higher dimensional case, it's a nonlinear version of that that also involves omega phi. Well, it's a long story. But we understand very well this space. And then the miracle is that the functional that we look at extends to this in a very nice way, I mean a reasonably nice way, to the completion and satisfies a convexity property. So that's the key here, because we are looking for a critical point of a functional. In fact, this functional is convex when you view it on the right space. Okay, so to summarize what happens here, we've got another result of Berman and Bernson, actually the same paper where they show uniqueness I mentioned before, that M extends in a canonical way to lower semi-continuous functional on the completion, but then it becomes possibly infinite at some points. And M is convex, is further convex with respect to a natural class of geodesics in the space H bar. So any 2 points in H bar can be connected to a canonically defined PSH geodesic, and M is convex along such geodesics. So then it becomes more plausible that you basically have a convex function, and you want to know when it admits a minimizer, and the corresponding condition will be some linear growth condition. But the minimizers are only unique up to the group TC that we saw before. So then the corresponding characterization is like that. So you take some so phi here, you take some phi like that. Okay, maybe I should say. Okay. What I want to say, yeah. So phi here is a minimizer. The first thing is that all the minimizers are regular. So phi is a minimizer of M, if and only if phi is actually smooth and omega phi is extremal. So of course, by the convexity, somehow if you just look at the open part, a minimizer should be a critical point, and then it will be an extremal metric. But here we want to say that, in fact, all minimizers have to be in the smooth part, and therefore still correspond to extremal metrics. So that's the regularity of minimizers part. And the second part, which is the thing we want to use here, is that there exists an extremal, so minimizer like that, minimizer as above, if and only if M satisfies some linear growth condition. So I've said before that M, the functional M, is invariant under the torus. So it descends to the quotient of our space. Well, there was a T actually everywhere, probably. It descends to this space, and this guy must have linear growth with respect to the metric, with respect to the quotient metric. So that's some, it's called coercivity of the functional. So it means you have an estimate like that. M of phi is greater than delta. You can find some uniform constants, delta and C, such that something like that holds all the time, and that's the quotient metric on the quotient space that we've been looking at. Yes?
Just a curiosity, is there something I'm missing, or like one, the regular minimizing is more Berman-Darboux?
No. No, Berman-Darboux, what they showed is that if you have one regular minimizer, then every other one is actually, it's more related to this uniqueness, but within the bigger space. They show that if you have a smooth minimizer, every other minimizer is still related to the other one by some automorphism, and so in particular is smooth. But here it's some a priori thing. You want to say that no matter what, any minimizer is in fact smooth, and therefore corresponds to the metrics that you're looking for. Okay, so just to say that the intuition behind that is really a one variable picture for a convex function. Once you pass to the quotient, this M can have at most one minimizer by the uniqueness we saw before. So if you have a convex function with at most one minimizer, then it will have a minimizer exactly when it grows linearly. Okay, because if it's at most one and you have a minimizer, it means a nearby point have to be higher, and then the function keeps growing at most linearly in the one variable case. So it's a much harder, of course, higher infinite dimensional version of this picture. So that's why you pass to the quotient to ensure that there can be at most one minimizer, because of course if you have a whole set of minimizers like that, well, the function could just remain flat always. So this is not happening because we pass to the quotient. Anyway, okay, so that's the deep, very deep technical, well, analytical input that we want to rely on. So in minutes, I will sketch the strategy of proof of this openness result that I've probably just erased. Anyway, so I will explain that in the case where you don't blow up, just to show how it goes. So it's a strategy that has been really around in the field for some time. It goes back to the work of Darvash again and Rubinstein, except that here we have a moving sequence of Kähler classes. So yeah, I should have said that linear growth condition here is called coercivity. Coercivity of the functional. So, okay, so you assume that the functional you've got for a given omega is coercive, satisfies the coercivity condition. So that means you're assuming that omega or somebody else in the same Kähler class is extremal. So maybe I should say, maybe instead of saying that, I can say you assume that omega is extremal, so that by the result we just saw, we have this coercivity condition. So then the plan show that this coercivity condition is preserved when you deform, when you move the class a bit. So you take a sequence omega j of Kähler forms that converge to omega, and you want that the corresponding functional, so hopefully with more or less clear notation, I put an index j everywhere for the sequence, and you want to see that the corresponding guy is still coercive for j, for j large enough. So this is not, this is not corresponding to the case of a blow-up, because in the case of a blow-up, the omega j's converge to the pullback of omega, and then we have to work a bit harder. It's just to get give some idea of what we do. So you argue by contradiction. You assume this is not true. So you argue by contradiction. Then you can find, if not, then you can find some phi j. Actually, to test coercivity, it's enough. You don't need the bar here. If you have coercivity on x, it extends to the completion by some approximation argument. So you can take some sequence phi j in hjt or the closure, it doesn't make a difference, such that coercivity, something that contradicts coercivity. So it will look like this. This is contradicting the coercivity of mj. Okay. And then you want to use some compactness argument to extract from the phi j's a limit guy phi in h of omega that will contradict the coercivity of m. So the plan is not particularly sophisticated. But the problem is, how do you get this compactness? And so what's happening is that, so I've dropped the fact that I need to pass to the quotient metric there for simplicity. So let's forget about the torus just for simplicity. Okay, so now what happens is that, remember that mj of phi j has this entropy part plus this energy part. So this guy here is non-negative anyway, it's the entropy. And this guy here is bounded in a linear way by the distance, controlled by the distance metric. Yeah, I should put a j somewhere. Yeah, sure. Yeah, with respect to omega j. Okay. So if you plug that in the inequality that we've got over there, you can see that the distance of phi j to 0 needs to go to infinity. So let me just draw a simple picture like that. So it means that the guys that are contradicting the inequality that we've got, they get further and further away in the space of potentials. So even if the class omega j was not moving, we can't really hope to extract a limit. So then the idea is to just look at what happens in some ball of fixed centered there by moving along the segment, the geodesic. Sorry. Okay, so you introduce phi jt, that's the geodesic connecting 0 to phi j. And then I've said before that we have this convexity of the functional along that. So this is a convex function of t. So what we know in particular from our estimate before is that mj of phi j is less than delta j times the distance between phi j and 0. And then this propagates all along the segment here thanks to the convexity of m. By the convexity of M, the estimate propagates like that along the segment. Okay, so I'm almost done. And then this can be used to recover compactness. So what you do is that you fix a T like that. You fix T, which will be large enough, but to be determined afterwards. But it's fixed, so it becomes. You've got some phi j(t) at this distance t when j is large enough, because this guy is going to infinity anyway. Okay, and then the inequality that we've got there implies that, so here I'm being quite quick, so you get some entropy bound. The right-hand side, you get some fixed upper bound for the functional M, so you get some, from that you get some entropy bound for phi j(t), and by some compactness argument, you can assume that phi j(t) converges to some phi t in the limit. But now if you pass to the limit, so there's some semi-continuity of M that I've mentioned before, and there is a version even when the class is moving. So in the limit you get an inequality like that, and this will be less than or equal to 0 by the bound there. And this contradicts the recursivity of M, because that's supposed to tell you that M grows at least linearly with T. It's supposed to say, to give you something like that. So if you take T large enough, you reach a contradiction. And okay, that's it. So let me just say that, yeah, it's a very sketchy proof here, but just to give a flavor of the sort of argument. So what we do is actually a version of that for the blow-up. And at some point, you need, in the argument for the blow-up case, which is the more interesting case, we need, in a crucial way, the fact that minus k of the blow-up is relatively nef. So in other words, we need at some point in a crucial way the fact that you can find some reference metric on y that can be bounded below by something coming from x. So the two conditions are equivalent, actually. And this comes as a very crucial condition. So then, as I said, it would be more interesting to look maybe at arbitrary modifications, or even a resolution of singularities, starting from x being singular, and try to run the same arguments. But then we run into this algebra geometric constraint that prevents us from applying that very broadly. So if you have like a crepant resolution, it's okay, but otherwise not. Okay, so I stop here, and thanks a lot.